In Module 5 of Chapter 13, we'll look at this market maker P&L analysis in a little more detail. What if, instead of the stock price moving by one standard deviation, it moves by a multiple of that standard deviation, where we assume the multiple has a standard normal distribution? So here we're hypothesizing that E, the change in the stock price, is the one standard deviation, and now Z has a standard normal distribution rather than being plus or minus 1. So we're generalizing this a little bit and going from a binomial plus or minus 1 standard deviation to a normally distributed value. We can then do the math, and we get that the P&L is a random variable. If we just insert this value of epsilon, it's a random variable, and the P&L with that representation for E, in fact, we see the Z here. It's a random variable. That the P&L is a function of Z squared. Some of you may know that if Z is normal, Z squared has a chi-squared distribution. So we see that the P&L is a random variable that depends on Z. We can calculate the mean and the variance of this random variable. The mean is easy because we know the expectation of Z squared is 1. So we can here calculate the expected P&L, and that's an expression we've seen before where we assume that Z is plus or minus 1. And this term by the Black-Scholes equation would be 0. So what one can say is that the expected value of this random variable is 0. And then we can calculate the variance of this random variable by subtracting the mean from pH and squaring it and taking the expectation. So we now need to know, in order to calculate that, what's the expected value of Z squared minus 1 squared? Well, we can just multiply out Z squared minus 1 squared and recall that the expected value of Z to the fourth power, is called the coefficient of kurtosis. And for the standard normal, the coefficient of kurtosis is in fact 3. So we can do the calculation and we get the number 2. And what we finally conclude when we put it back together is that if we assume that stock prices are a normal random variable times a standard deviation, then in fact the variance of the market maker's profit and loss is proportional to H squared. The importance of this is it says if the market maker rebalanced, divided the period H into n subperiods, the variance of the sum of the P&Ls would be 1 over n times the variance of the one period P&L. So by virtue of dividing the period in half, say, that cuts the variance in half. And so we saw this in the book where the hourly variance, by rebalancing hourly, we get 1/24th of the daily variance. This is just an example of our general formula. And so what this tells the market maker is that, and of course if I looked at standard deviation of the P&L, it would go by square root of 1 over 24. And what this is saying is that the market maker can, if the market maker rebalances every nth of a day, he reduces his standard deviation of profits and losses by 1 over square root of n. So there's an impact on the volatility by rebalancing. And the conclusion, as you might suspect, is that by more frequent rebalancing of the delta hedge, the market maker can eliminate or reduce the gamma losses that are sustained, and that's because frequent rebalancing allows the stock to move only by smaller amounts because of the associated distribution. But this analysis does ignore transaction costs. In reality, the market maker has some transaction costs, and there it's impractical to rebalance too often. So there's a tension between, on the one hand, frequent rebalancing is good for the market maker because it reduces the gamma costs and ultimately reduces the variability of their profits and losses. But on the other hand, there will be a cost item associated with that rebalancing associated with transaction costs.